Okay, moving right along, Unit 11, sound. So all sound waves are longitudinal in nature, so I'll circle that. The definition of resonance is two frequencies that cause amplification. So if you have two things that are coming back and resonating or getting louder, what controls the speed of the sound? It's really the elasticity of the media, but also we also found out that temperature is a major factor. Here's an example of a sound wave where you have, compression, rarefaction, compression, refraction. So the or the particles get bunched up and spread out. Compression is where it's bunched up. So this compression is up here and this rarefaction is down here in terms of the pressure. Speed of sound is always the same thing. It's 343. The velocity of the string equation, square root of the tension in newtons divided by the length in meters and the mass in kilograms. And as far as pipes go, we can have an open pipe. Here's the fundamental. Here's the fundamental of a closed pipe. These end in halves, these end in quarters. So an open pipe, we say 1, 2, 3, where L equals a half, L equals 1, L equals 3 halves. Or even harmonics. These are odd harmonics. So we have the first, third, fifth, 1, 3, 5 closed pipe. We go 1/4 of a wave, 3/4 of a wave, and 5/4 of a wave. They occur in odd harmonics. Wow, I wasn't even on the screen. Okay, so that's it for some of the review. All strings will always vibrate in such a way that they have nodes on each end. Here would be the first wave, would look something like that as it's bobbing up and down. And so the first thing we have to do is find the velocity in the string. So we use our equation for that, which is right here. So the tension in the string was given with 7, and the length of the string was 75, so 0.75, and the mass of the string is 0.09 grams. And then you multiply it out in square root, and that'll tell you the velocity in the string. So when I do that, I get 7.64. Let's just double check it. 7 times 0.75 divided by 0.09 square root. 7.64. So that's the velocity, 7.6. That's the velocity in the string. And then from the velocity, we can find important other things like the wavelength. And then from the wavelength, we can find the frequency. So velocity equals frequency times wavelength. So the velocity in the string is 7.64. For the fundamental, the wavelength, we go back over here, would be L equals 1/2 of a wave, or 2L. Wavelength equals 2L. So 2L would be 1.5, 2 times 0.75. So that would be 7.64 divided by 1.5. 7.64 divided by 1.5 will tell me my frequency. .09. So that's the fundamental, is 5.09 hertz. Then I can also find the first overtone. So that's the same thing as saying the second harmonic. So I could just multiply it by 2, be the easiest way to get that. And then I get 10.19 for that one. Pipes, in my opinion, pipes are even easier. This is a closed pipe. In the closed pipe, we start with a node and end with an antinode. So V is always 343 because it's air that's doing the vibrating in this kind of pipe. And then I have my wavelength and my frequency, Want to know what frequency is? Wavelength we know for closed pipe is 4L. So 4 times the length would be 4 times 4, or 16. So frequency equals 343 divided by 16. 21.44. That's the first one, and then the second overtone would be the same as the third harmonic, so if I just multiply that by 3, I get 64.3. And then it would go up to 107.9, but whatever, it doesn't, you don't really need to know that. So that was sound, and that's 10%.